Okay, this highly sophisticated demo is going to illustrate to you the importance of vertex distance. So this is an eyeball, and here is a plus lens. And you remember parallel light comes in, the plus lens converges it, and since we have the right prescription, it converges it right onto the retina. So this is beautiful, the patient's happy. If they move their glasses too far away, the image comes to a focus in the vitreous, and then you can imagine these lines carry on. It hits the retina, it's blurry. So if they slid their glasses down their nose, it would be blurry in the distance. If they smash the glasses closer to their face, they're going to be, the image will come to a focus, if it could, behind their eye, which means when it hits the retina, it'll be kind of blurry. So here's where it should be to correct this patient's farsightedness. But if we move the lens closer or further to the eyeball, the focal point of the lens goes with the lens. So it just moves whichever direction you're moving the lens. So that's what happens when you adjust the vertex distance. Now, in this little demo, we have the same patient, but we put on a stronger lens instead of this power of lens that came to focus right on the retina. We said, we're going to over plus them, give them a ton of extra plus. That converges the light too much, and it's in focus in the vitreous, which kind of makes them feel like they're nearsighted. By the time the image gets to the retina, it's blurry. However, if they took these lenses that are too much power and smashed them onto their cornea like a contact lens, it would work just great. It would be in focus on the retina. So for a contact lens wearer, we need a higher plus power because the lens has to converge the light in a shorter distance than with the glasses. The light has to converge on the retina, but the lens is a little further away from the retina with the glasses than with contact lenses. Now, if somebody's looking at something up close, the diverging light, the plus power lens can't converge it as much as it would converge parallel light. Parallel light enters with 0 power, and then whatever the power of the lens is, it converges to its focal point. But if you start off with diverging light, the lens, same power lens, can't converge it as much, and so it ends up back here, and the patient can't read. They either have to accommodate to move that image to their retina, that would make this lens stronger, or they can slide their glasses down their nose, which is why old people slide their glasses down their nose to be able to read, because they drag the image from behind the retina onto the retina. So that's why sliding the glasses down the nose works, whether it's plus or minus power lenses. That works beautifully. Now, so that's plus lenses. Here's a myope. And myopes are harder to draw, but the parallel light comes in, it hits the minus lens, which causes it to diverge. And then we have to actually, in our illustration, take into account that the eyeball really does have power. We like to ignore that, but you just can't draw it with minus sphere lenses like that. So anyway, this is a properly corrected myope. The image is right on their retina. If they slide their glasses down their nose, it's going to put the image in the vitreous and they'll be blurry. If they are under minus, they will smash the glasses to their face, because that makes it a stronger, well, it gives them more power. Let's put it that way. So if you have a myope who's smashing the glasses up their nose, it's telling you that they don't want it away, they want it as close as they can, but my demo doesn't show that. We have the myope who is looking at something up close. Same idea, the light diverges, so when the minus lens diverges and then the eyeball converges, it just doesn't have as much power. The image ends up further away, just like it did with the plus lens. And this myope is going to do the same thing to get that image on their retina. They're either going to accommodate, which I can't draw, or they're going to slide the glasses down their nose, which I can draw very nicely. So this again illustrates why old people slide their glasses down their nose. And then let's say I don't have a nice demo to show you why we need lower power for myopes and contact lenses, but believe me, we do. This might do it. Here's an under minus myope, vitreous image comes into the parallel light, goes through the lens, comes to focus in the vitreous. If we smash the glasses closer, it moves the focal distance closer and puts it on the retina. So this would be either an uncorrected myope who really needs more power in the glasses, but they can just smash them toward their face and get more power that way, or the glasses playing, it doesn't illustrate it very well, but basically if you take this minus lens and move it onto the cornea, it gets the image on the retina. So that's what that does. So Vertex, distance, easy to show you with plus, harder to draw with minus, but very important, particularly the bigger the power of the lens. So for a plus or a minus 2, who cares? Doesn't really matter where the lens is, but for a plus or minus 10 or 15, it makes a humongous difference, just a millimeter back or forth of how the glasses work for the patient. So it's something you need to be very aware of with glasses, frames, fitting, and also with contact lenses. Once it's a greater than a plus or a minus 4 is when we clinically start to take into account the difference between the spectacle plane and the corneal plane. And we think that's standard, about 12 millimeters is what we use clinically. But really, if somebody has deep set eyes or shallow set eyes, it would not be 12 millimeters, but that's kind of the default. So there you go, Vertex distance.